Hey. Hey. Alright, so what we're going to talk about today, at least in this little module, is system properties and Z transforms. Alright. So what we should have talked about a little bit last time is, what is a Z transform? I think we've been talking about the last couple of days, recording these things out of order, so it's a little bit difficult to figure out what people have done. But let's just recall here that if we had an impulse response, h of n, of course we're working in discrete time, the corresponding Z transform, the Z transform is given by sum as n goes from negative infinity to infinity, h of n, z to the negative n. And we denote this by h of z. All right? And so what we're going to be doing in this lecture is figuring out how, this is kind of, sorry, so I was just checking to make sure that everything was actually looking all right. And it is. So back to where we were at. We've got this Z transform, which we'll refer to as our transfer function. Right. And just as a quick refresher, let's just go and work out a basic Z transform. And remember, just like with our Laplace transforms, the Z transforms have a functional form, but we also need to know what the region of convergence is. So let's go and look at this. Say h of n is equal to 1/2 n u of n. So everybody go ahead and calculate out what is h of z and draw its region of convergence. It's ROC. All right, so class, everybody do this. Calculate h of z and draw its region of convergence. All right, TA, stop the video. Stop not stopping the video and stop it. Okay, start the video now. Okay, good. All right, so now everybody's back. I'm sure that we've seen most people got the calculation correct. And presumably we'll have all gotten the regions of convergence correct. And what we have over here, so this down here is our h of n. And the goal was to calculate the h of z and draw that region of convergence. And so our h of z, first off, is equal to sum. So when we see this u of n, what do we need? It's u over there. Change the bounds. That's right, change the bounds. N equals 0 to infinity. 1/2 to the n, z to the negative n. All right? And we can look at that and we can use our handy formulas to say, well, this is 1 minus 1/2 z inverse. And I'll put little things there so that my z's look a little bit less than my 2's, or a little bit different than my 2's. And the region of convergence is every z that has magnitude greater than 1/2. So if we draw this out here, it's always going to be, we've got this thing up at 1/2. We're going to draw out our circle of radius 1/2. That is not in our region of convergence. It's everything strictly outside of this 1/2 is our region of convergence. This is the region of convergence. And again, remember, when we're looking at these pole zero plots, kind of similar to what we had in the Laplace transform world, when we look at the pole zero plots, what we're always going to have as our region of convergence are little disks that live outside of where the poles live or inside of where the poles live. All right, cool. So there is, of course, another impulse response corresponding to this that gives rise to the exact same transfer function So there's another impulse that gives rise to this exactly, but it's going backwards in time. So let's just very, very quickly, don't pause it for too long, just kind of make sure that everybody's going on. Let's very quickly figure out what is that thing? What is that other impulse response that gives rise to it? And that is, and what's its corresponding region of convergence? All right, so pause it just real quick. All right, I don't know why I'm waiting that long, but come back. All right, so I saw fewer of you getting this exactly right, and what it is, right, we'll just recall. So the other region, the other impulse response corresponding to this is h of n is equal to negative 1/2 to the n times u of negative n minus 1. Right. Let's just really quickly work through why that's the case. All right. So sum n is equal to 0 to infinity h of n z to the minus n, and we plug it in. What do we do here? We change the bounds. And so we need what's in here to be non-negative. So we need negative n minus 1 greater than 0. So this is how we're going to get the bounds. And so this is going to be n less than negative 1, or the sum as n goes to negative infinity to negative 1 of negative 1/2 to the n, okay, z to the negative n. And then if we do a bit of futzing around with this sort of thing, we can do a change of variables up in here. And so we're going to say, oh, well, this thing is actually equal to sum negative. If we let n is equal to negative m is equal to 1 to infinity. And then it's going to be z times 1/2 to the 1, so it's going to be, let me just write this here. Let's not skip steps. Even though I'm not actually there, we still don't want to skip steps. Z to the m. And then we can go and pull this thing out, and we're going to get 1/2 z. M is equal to 0 to infinity times 1/2 times negative mz to the m. Looking like that, okay? And let me just continue this over here. Unfortunately, I don't have nearly as much board space here as I have normally in class, but what we can use here is we're going to be taking this sort of thing to be the z. So if we go and rewrite this thing, let's just go and rewrite this a little bit more explicitly. This thing is equal to negative 1/2 z times m is equal to 0 to infinity times, so this negative m just gives us a 2, so it's 2z to the m. And so what we're going to be corresponding to having is z's that live in here, so that this thing is less than 1. And then we're going to have 1/2 z. And then let me erase this thing. It's just so little board space that we have. We get 1 minus 2 z right up in there. Oh, I made a mistake here. I needed to pull out a minus 1 here. There we go. And so we need a 2z, a 2z over here. And then with just a little bit of rearrangement, we can see here that this is actually equal to 1 minus 1/2 to the z inverse by just doing a tiny bit of rearrangement. Maybe take a pause, convince yourself of that, but it's true. Okay, well, I'll just go and do it, because otherwise there's a chance that you may not go and do it. So this thing is actually equal to, let me stop this. Okay, we're back. So sorry about that. All right, so where we left off was we got this thing up to here. So we got this funny form. And let's just go and see that, oh, well, this thing is actually equal to, because we want to get it in a form that looks like this. So 1/2 z inverse is actually equal to 1 over 2z, right? That's pretty straightforward. And so we can see that up here, this thing is the same thing as multiplying the bottom. This multiplying the top by 2z is the same thing as multiplying the bottom by 1 over that thing. And so we get negative 1 over 1/2 2z minus 1, which is equal to 1 minus 1/2 z, which is exactly what we wanted. All right, cool. So that corresponds to the same exact transfer function, but with region of convergence living in here, because as we discussed, this thing is going to have to be less than 1, and it lives up in there. So we've got these two things that give rise to the same transfer function. Now, let's go and look at these for a second. All right? So let's take a step back, and let's think about the property of causality. All right? So keep that in mind. We're going to have to erase this, and we're going to remind ourselves of what is a causal system in discrete time. I'm going to just keep those things that we had up here. H of z is equal to 1 minus 1/2 z is z transform of h of n is equal to 1/2 to the n u of n, and h of n is equal to negative 1/2 to the n u of negative n minus 1. All right. And so remember, causal systems, let's just take it a step back, are ones that don't depend on the future at all. And so very similar to what we had in continuous time, in discrete time, an LTI system is causal if its corresponding impulse response, its impulse response has h of n is equal to 0 for n strictly less than 0. Now let's just draw it out for this particular example. So in particular, which one of these things is causal? Well, it's the one that's 0 for n less than 0. And so it's going to be this one up in here. So let's draw that out. So if we draw little marks up in here, it's going to be 1, 1/2, 1/4, so 0, 1, 2, 3, and so on. Da, 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 da. And then 0 everywhere else. And this is h of n is equal to 1/2 n u of n. And so this is causal, and we can think about it, and remember, what is the impulse response? It's the response of the system to an impulse. So we put an impulse at t is equal to 0, boop, and then it goes okay. So that's our causal impulse response. Whereas if we looked at this thing over here, this is going to have an impulse response that looks like this. So it's going to be, you know, -2. So I have to draw it a little differently. So n, so down in here, if we have 0, 1, 2, it's going to go at -1. It's going to be at -2, -4 down in here, and then so on that we can't draw because the board is small. This is for the system that is -1/2 1/2 to the n u of negative n minus 1. So this is what's called strictly anti-causal, actually, because what happens is we apply an impulse at n is equal to 0, and all of the response came before that, strictly before that. So for discrete time, we have what's called this strictly anti-causal impulse response. And if we go and relate these things to our pole 0 plots, this thing went and we got our pole up at 1/2. This is the region of convergence going out here, and this is a region of convergence living inside here. So remember, whenever we're doing our pole 0 plots, we're plotting them in the complex plane, meaning that we've got the real axis here and the imaginary axis here. So if we drew this out, this would be 1. Up here would be j over 2. Over here, this would be 1/2 out here. This would be j over 2. So the key feature that we have, okay, is that for causal systems, we have that the impulse response, all right, goes forwards in time, meaning that it's 0 everywhere, and then it's non-zero only as n is greater than or equal to 0. Right? And corresponding to that, whenever we draw out these z transforms, what we have is that everything outside of some ring is part of the region of convergence. So that's the key feature here. For causal systems, corresponding region of convergence corresponds to everything outside of some ring. Now, for these anti-causal systems, what we're going to have over here is that for anti-causal, everything takes place before n is equal to 0. And when we draw the region of convergence, it's a little disk containing the origin. Okay? This right here is this little disk of radius 1/2. It doesn't include 1/2. It's everything just outside of 1/2. And it lives up in there. So in particular, the takeaway message here is that for causal systems, we have outside. For anti-causal systems, we have going inside. All right, let's take a moment and do one more example. Okay, so we're going to deal with a bit of slight generality. We don't usually do a lot of general proofs, but let's do a little piece of, a general proof. In particular, I want to show that if h of z is the transfer function of a causal system, and R0 is in the region of convergence, then z, for all z, such that z is greater than R0, we have z in the ROC. So the geometric picture that we have of this statement is simply that if we had a region of convergence that looked like this, with some where we knew that some R0 was in the region of convergence, so we know that the region of convergence is always some ring that looks like this. So if we knew that this R0 over here in the complex plane, R0, was in the region of convergence, then that's going to tell us that everything outside of this R0 must also be in the region of convergence, meaning that everything out here, all of this stuff, must be outside the region of convergence. And this is a very general statement here, because we're just saying we have a causal system, a causal linear time invariant system, I should say LTI, and we've got this R naught out here in the region of convergence, then everything outside of it must also be in the region of convergence. And this is actually pretty straightforward to do, because if this R naught is in the region of convergence, then we know the following must be true. Well, two things. One, it's strictly causal. So what does that allow us, well, not that it's strictly causal, but it's causal. So what does that allow us to do? Change the bounds, right? So in the end, that's telling us that the impulse response is only non-zero for n is equal to 0 and later. So we can automatically write our h of z is equal to n is equal to 0 to infinity h of n, z to the negative n. And by knowing that this R0, so what I'm doing is I'm just proving this statement, all right? What we know is that R0 is in the region of convergence, and so R naught in ROC, that's just the in sign, implies that the sum is n from 0 to infinity h of n. This sum that we have right here absolutely converges. So meaning that if we take this sum from 0 to infinity, this summation converges, and it converges to something less than infinity. All right? And so now if we had z greater than R naught, so any z out in here, we must have, by just doing a tiniest bit of rearrangement, R naught n greater than or equal to Zn. Right? Because all this is doing, we can just raise this to the n. This thing tells us that z to the n is greater than R naught to the n. So anything out in here, then we've got that. And so that's going to tell us that n is equal to 0 to infinity h of n, z to the minus n, is less than or equal to n equals 0 to infinity h of n R naught minus n, which is less than infinity. So indeed, all of these things must be in the region of convergence. So that's just kind of lets you know here, if we've got a causal system, we always know our region of convergence lives out there. And the exact same thing can be shown for these anti-causal systems. If you had an anti-causal system, then we know that the region of convergence is going to be some disk containing the origin, whereas this is some, like, you know, it's the plane with a hole in it, basically. All right, cool. So that's the basics of causality. Now, the next topic I'm going to want to talk about is stability. Now, we talked about stability in discrete time, but we didn't talk about it all that much. All right? So we're going to go and do a little bit of an excursion into stability theory for discrete time systems, because we just haven't really done it before. I mean, we did it, but only like just, you know, for a few minutes. All right? So stability of discrete time systems. All right? And so one of the things, one of the main things that we're going to see here is that the two punchlines of this is we're going to see that a discrete time system is stable if and only if the unit circle is in the region of convergence of its transfer function. Discrete time LTI system. Of course, we're always dealing with linear time invariant systems here. A discrete time LTI system is stable if and only if, that's just saying that, you know, if and only if the unit circle is in the ROC of its transfer function. And then the other thing that we're going to see here is if h of z is rational, it is stable if and only if all poles is, okay, if it's rational and causal, if the system is causal, if the system is causal and h of z is rational, so we're going to see that that shows up all the time. Remember, that was like one of the things we had was 1 over 1/2 to the z. That's what we started with. That's a rational function because we can write this as polynomial over polynomial, right? It's z minus 1/2. So that's got a 0 at the origin and a pole at 1/2. So this is stable if and only if all poles lie strictly inside the unit circle. Inside the unit circle. Right. So that's what we're going to want to show. And the basic thing just comes from the fact the relationship between these two is fairly simple, right? So if we have a causal system, remember, if we have a causal system, its region of convergence always looks something like this. The region of convergence always looks something like this for some radius r, and we know that if we have the rational function, the region of, if we have a rational function over here, where the region of convergence lives is going to be always either to the inside or to the outside of the poles. But because we know this thing is causal, we know that the region of convergence has to live outside of all the poles, and so in particular it's going to look something like this. Say we had poles over here. So if we have poles over here, the furthest ones out are going to dictate where the region of convergence is. And so if we want stability, then we're going to have, by this property up here, the unit circle living in the region of convergence. So if this is the unit circle over here, out at 1, j over here, if this is the unit circle, we're going to need to have that all of the poles live strictly in the unit circle so that the unit circle can be contained in that region of convergence. So in particular, once we understand how this works, then this is just kind of automatic based on what we saw before. Because we saw that the causal systems always kind of lived out here, and we saw from the stuff that I'm hoping that we get to on Friday, that when we have these systems that are dictated by poles and zeros, that they're always sort of, you know, the location of the region of convergence is always dictated by being outside or inside of where the poles are. So let's go and try to work this sort of thing out by first going back and thinking about what does it really mean for something to be stable. All right. So kind of jumped the gun there a little bit, but that's okay. Stable, the basic idea is you put in any bounded input, you get a bounded output. So en route to showing this sort of thing, a system is stable if every bounded input leads to a bounded output. All right, so what we're going to do here is sort of illustrate with an example that lets us know that we're going to show the following statement, but we're not going to do it in its gory details, but we have the following statement. An LTI system is stable if its impulse response satisfies some n equals infinity to infinity, Hn less than infinity. So in other words, its impulse response is absolutely convergent. So this is just another way of saying that this thing is absolutely convergent. Okay, so this, all right, we don't even, once we know this, that these two things are equivalent, then this statement becomes immediate. Why does it become immediate? Let's just take a stop for a minute and just discuss amongst yourself why this is immediate. Okay, bring it back. Okay, this thing is the exact same thing as saying that this statement right here is the exact same thing as saying that n is equal to negative infinity to infinity e to the negative j omega n h of n converges to something finite. So in particular, that means that all of these things along the unit circle must be in the region of convergence. All right, and I'll be back. I've got to do a discussion section. Okay, bye. I'm back from teaching that discussion section. So what we're going to try to do is we're going to really try to go and work through why this is true. Because as we saw, if this absolute convergence condition is satisfied, then that tells us that everywhere along the imaginary axis, the Fourier transform converges absolutely, or in other words, the Z transform converges everywhere along this imaginary axis. So this statement that this is contained in the region of convergence and this statement that the absolute value converges are the same exact thing. So let's just work through an example and try to figure out why this is true. All right, so first off, well, we'll show sort of one direction that if it's stable, this is definitely true. So actually, the crux of the entire general proof is the following thing. So given, and this is going to be a challenge problem for you guys. Given n, so a specific value of n, given a specific n, and h of n, the impulse response, find x of n such that, so I'm going to say n naught, all right, such that y of n is equal to x of n convolved with h of n, such that y of n is as, well, such that as big as possible and x of n is less than or equal to 1 for all n. All right? So the goal is we find something such that is big as possible, at y n 0. So what we're trying to do is make this as big as we can possibly make it by choosing an input that's less than 1. So step back. X is our input. This is the corresponding impulse response. We're trying to make the output as big as we can make it at n naught with a bounded input. So stop. This is a challenge problem. So challenge yourself. All right, so that one was a toughie, but the main thing that we need to do, if you haven't gotten it yet, we may need to stop the video again. So if we haven't gotten it, just stop the video and everybody go down and write down the convolution formula. What is yn0? All right, let's write down. What is yn0? Okay, so I'm assuming now everybody has what yn0 is. It is equal to this. M is equal to infinity to infinity. All right. H of n0 minus m times x of m. And we want to make this as big as possible with x in with this thing less than or equal to 1. Well, what we can always do is we're going to choose xm is equal to 1 if h of n0 minus m is greater than or equal to 0, and negative 1 if h of n0 minus m is less than 0. And then the 0 case actually doesn't really matter, right? Because if you have this thing is equal to 0, 0 times anything is 0. But this thing definitely has xm has magnitude less than 1. And we got this. If we had h was a complex, this is assuming that h is a real signal. If h were a complex signal, then what we would really do, sort of more generally, we would have x of m is equal to e to the negative phase of h of n0 minus m. This is going to be a general case, more general case of this exact thing. All right, so this will work for general complex signals. Now the key feature is when we choose this as our input, what is actually going to happen here is that this thing is actually going to be equal to, so if this thing times that is positive, and it's just positive this. If this thing is negative, we multiply by negative 1. So we got negative of this. This is actually the absolute value. So this is m is equal to negative infinity h n0 minus m absolute value. Right. And so the key feature here is that we can always make this thing, if this thing is bounded, then doesn't matter how we choose this, it doesn't matter how we choose this x of n, this thing over here is always going to be bounded. But if this thing was not absolutely convergent, so this thing, remember that n0 doesn't actually do anything for our signal. This thing is actually equal to some as, well, actually no, it actually does matter. So we gotta keep that in here. Actually no, it doesn't actually matter. So it's m is equal to negative infinity to infinity h of m. Right? So it turns out then that if this thing is bounded, then that means that for all of the inputs we can possibly get, we're going to have a bounded output. But if this thing is not bounded, then by choosing our inputs this way, we're going to make it. We're going to make this thing go to infinity. We're going to make the output go to infinity at a particular n0. Okay. So that's basically how this works. So yeah, that's it. So that is essentially the proof. What we've shown here is system is stable if and only if and only if this thing is absolutely convergent, which is true if and only if the unit circle is in the region of convergence of that Z transform. So this actually tells us a lot, right? So in particular, we can go and just sort of look at a pole zero plot, or look at a system and just look at its poles, and we can tell which of these things correspond to stable and rational and so on and so forth. So let me just do a few examples, and then you can work them out for yourself. So So let's see which of these pole zero plots correspond to stable systems and causal systems. All right. So I'll just start drawing some pole zero plots and you just start working it out. And I'm going to draw the corresponding regions of convergence. So that's the first one. So I got 1 out here. I'm going to have this at -2 over here. And the region of convergence being here, 2. So I want to see what of these things are stable, which things are causal. And then we'll do just one more down in here. All right. Kidding. Well, actually, yeah, that's probably enough. My board is getting rather ugly. So, all right, stop. Let's work through all of these. Okay, start it back up. All right. So let's think about which one of these are stable. So is this one stable? Well, yes, because it's got the unit circle in there. Is this one stable? Well, yes, because again, it's got the unit circle in there. Is this one stable? Yes, because it's got the unit circle in there. All right, cool. So that's really easy. Just looking at that plot, we can tell which things are stable and which things are causal. Now, what about causality? So is this one causal? Yes, because it covers everything outside of this little disk right here. What about this one? Well, no, because this stuff out here is not part of the region of convergence. It's only the stuff in here, so it can't be causal. And finally, this thing, not causal, because it's only the stuff inside this little annulus over here and not the stuff out there, so it can't be causal. So in particular, this is going to correspond to something. So this function is going to correspond to one part that goes forwards in time. So everything outside of here is going to correspond to a causal piece, and everything out here is going to correspond to an anti-causal piece. So it turns out that the corresponding impulse response, we're going to be able to decompose it into a causal and anti-causal part due to the fact that we've got something going out and the fact that we've got something going in. All right, so that's it for today. Okay, bye.